But what I'd like to do initially is just go through some first principles. What we find there's a huge spectrum of people's knowledge and understanding at the moment. So if I'm teaching some of you to suck eggs, my apologies, but at least perhaps it will give us something of a common language and maybe even some room for debate. So high performance buildings. So maybe a good starting point is, well, what is high performance? That's a pretty good start. Well, MET like to think that it's about low energy use, it's about low carbon, which we're kind of familiar with, but also user health and comfort, which is often seems to be completely off the agenda. Why high performance? Pretty straightforward, as we know, rising energy costs and also legislation, two key drivers that are moving this forwards within our industry. Okay, so why rising energy costs? Okay, don't know how familiar you are with the term of peak oil or peak gas. So basically UK has produced less North Sea oil and gas since its peak, just should have said peak, in 1999 and 2000 respectively. Okay, so it's 2000 for peak gas. Since then, okay, we are now net importers of 60% of our gas. Okay, it'll probably be about 80% by 2020. Your average fuel bill will probably be 3 to 4 times what it is today by 2020. So reasonably significant driver. Okay, now fossil fuels deliver 90% of our energy, so it focuses us a little bit more. But the trick with fossil fuels, and this is the mistake often made, it's important to understand that when we're replacing a fossil fuel with a biofuel, an alternative, maybe a renewable energy source, it's not quite the same as replacing apples with apples. Okay, principal reason, give you a quick example. Ton of wood chip, okay, 35% moisture, that's because what usually the moisture content of wood chip as it goes into a biomass boiler delivers about 2,600 kilowatts of power, okay, depending on type or species. Oil's a little bit more, okay, per ton. So to give you another analogy, the amount of energy in a single barrel of oil is the same as 5 men working non-stop for a year, okay? So what we need to understand is fossil fuels are incredibly energy concentrated, incredibly energy dense, and that's the trick that we often miss. So actually it's not a simple matter of just switching to an alternative, because there's not that level of concentration out there anymore. It's just a physics fact. It's not a technology issue as such, it's a physical fact because we just don't have that energy in concentrated form. I'll come back to that later. Rising energy costs. Legislation, for whatever reason, the government's decided to go for a carbon-based legislation, and the reason behind that is we've committed to an 80% carbon reduction by 2050, and we're in fact the only country on the planet that's decided to sign up to that on a legal basis. So we are legally bound, folks, to deliver that by 2050. Okay, and because the built environment attributes pretty much 50% of the CO2 into the atmosphere, it's the biggest hit, and therefore it's the biggest drive to deliver on legislation. There we go, 48%, was pretty close. So we would argue, and I think you probably agree, these changes necessitate a new approach to building design and building construction. And that really, actually, we're in a phase of research and development. Now, you guys as architects and practitioners are probably a bit more familiar with thinking of alternative ways of actually solving a problem, but the reality is the construction industry is actually very conservative. I'm sure I don't need to tell you that. And the idea of change and research and development is pretty limited. Okay, the amount of research that's based even on what happens to moisture within building fabric is incredibly limited. And legislation isn't exempt from this. Okay, so BREEAM, SAP, Code for Sustainable Homes, which probably won't be with us much longer, Green Guide, etc. Important to understand they're not, please don't use them as design tools, okay, because they're also very much a work in progress. Okay, they're getting us there, they're useful to rough sort of boundaries, if you like, to where we need to be headed, but they're changing all the time. We've seen companies get the rug pulled from under their feet because they've gone a particular way, aligning themselves very closely with delivering, say, code 5 or 6, only to find it's changed when we hit the 2010 regs, and it's going to change again when we lose the code altogether. FIT scheme, you know, the feed-in tariff, that's a very simple example illustration of that. The other thing that I'd flag up as well is, probably could have done with a different slide on this, but I don't know if you guys are aware of what's called the performance gap. Okay, it's becoming more and more of a real awareness issue, which is basically, in simple terms, 50% of our new builds, and that's mainly domestic stock, actually fail their as-designed SAP in real energy terms. Okay, on the bit of paper, it says yes, it'll use so much energy, but in reality, it's failing. Okay, by 2016, the government is hoping to introduce actually legislation that will measure the actual energy performance of a building once it's actually built. okay, in the same way that we have air pressure tests and we have acoustic tests today. So we perhaps suggest a proactive rather than a reactive response to all of this. Just a bit more about energy and carbon and how they kind of link together and the cost behind them. This was a bit of work we did some years ago now for Cornwall Housing Association, development down in St Austell. They wanted to deliver a zero carbon development, and we said why, and they said we don't know, but it sounds good. So we said okay, well, let's try and unpack that a bit. So we just produced a simple graph really, which illustrates pounds spent for carbon or tons of carbon saved. So that's this line here up here. And the first two measures here, there's a group called the ACB, Association of Environmentally Conscious Builders. They've been kicking around for quite a while now, but they've certainly come to the fore in recent years and actually help a lot with government legislation now. They produced a couple of standards called ACB Silver and ACB Gold. ACB Gold is not too different from Passive House, but there are some differences. But basic premise was, as with Passive House, it's all about the building fabric. It's all about actually reducing the amount of energy we need first. Okay, and actually they're the most effective, frankly, at saving carbon. Next to that, low energy lights, user appliances, user awareness, that's a biggie. They don't save the same amount of carbon, but in terms of as a cost-effective strategy, proved itself number three. And then we're getting into the kind of ground source heat pumps, micro wind, which I think most of us are aware of now, unless you're in the middle of a Scottish moorland, there's a bit of a dead loss. And even solar PV. This has come down a little bit, but not as much as we think, which is again part of the reason why FIT disappeared. Now the reason why those are so effective is simply because of this, average energy use in a domestic dwelling. Okay, so the vast majority of your energy use, 66% thereabouts, is actually space heating. All right. What I always find fascinating about this slide is we're always banging on about low energy lights, but in a domestic setting, actually it's only 3%. That's consumer lights down there somewhere, lighting down there. And of that, there's a further breakdown there. So you're seeing that sort of where it's actually proportioned to. So this is air leakage, external walls, so on and so forth. And just to give us an idea of putting that in a bit of context in terms of what we need to do in terms of delivering a low carbon strategy, but also really trying to respond to the fact that we need to use less energy, is where we are today. So this is a typical semi-detached property. The blue is space heating, the red is water heating. This is where we were in 2006 building regs. This is where we are today. This is where ACB Silver is, which was that slide earlier I showed you, and this is Passive House. So building envelope design, okay, the fabric of the building, the shell of the building, is now become widely understood as the most effective route to low energy design and low carbon design. Okay, MBT, quick introduction. UK's leading supplier of sustainable building systems for the building envelope, and we'd like to think we're a leading authority on building envelope design per se. And we basically have developed systems or a solutions approach for reasons that will become obvious hopefully later. New build, we've got Pavaroof, Paverwall and Thermoplan, and for retrofit coming under Pavercare, we've got Paverwall and Pavaroof again, but they're the R version. Okay. But what we also do alongside this is we have a project managed approach. Okay, so rather than just saying here's a piece of material, good luck, or we might do a U-value calc for you, it's actually a project managed approach where one of our guys will actually walk with the person through the project. So the client, the contractor, on-site training, the whole 9 yards. So it helps you at the design stage, the tender stage, the supply stage, and the contractor training stage. So it's a much more joined up thinking because we don't think that you can actually deliver the performance in reality unless you start joining some of these dots up a bit more comprehensively. So we've banged on about importance of building envelope. Might be worth just saying what are the key factors to all of this. We think there's probably 6 as a starter for 10. U values, I'm sure you're familiar with that. That's the principal heat loss through building fabric. Y values, are you familiar with that? It's in SAPMOR now. It's basically the non-repeating bridging. I'll tell you about that in a minute. Air tightness, we heat the air leaves the building, we lose our heat. So U values, basic stuff, but people are still sometimes unaware of this. That's the U value there, 0.18 of the insulation. So if I just took a heat loss calculation through the insulation alone, that would be my U value. If I account for the fact that the timber stud's there and they conduct heat more readily, obviously, than insulation, then actually my U value is 0.2. But if I actually include the air gap above there, my U value is actually 0.24, 33% worse than where I started. So actually understanding the whole picture of what's in my principal section of wall that's on a regular basis is quite vital. So always check quoted U values also include all common or repeating thermal bridges, studs, rafters, etc. Y values. Notional value, it's added to the U value and has become particularly relevant in SAP 2010, and has also, for us, has catapulted us from being a little bit more niche in terms of sustainability, in terms of being directly competitive, in terms of commercial cost viability, and I'll come on to why that is in a minute. You basically, these are all the kind of non-repeating bridges where you get junctions between principal fabric, and you calculate the Y value by taking a psi value, which is a two-dimensional slice through the bridging detail, and then you multiply. Actually, I'll come on to that in a second. The reason why it's more specifically important at the moment is this is the typical heat loss that we used to have. So this was the blue areas, sort of windows, doors, roofs, that sort of thing. The red area down here was the heat loss through the non-repeating bridging. When we get down to even part L now, the 2010, our heat loss, our principal heat loss, is reduced quite dramatically. So proportionally, our non-repeating bridging is suddenly much greater, up to 25% of your heat loss. So we need to now start doing something about that as well. And the way we calculate it, to finish my sentence from previous, you take a psi value, which is a two-dimensional slice through a particular junction. You multiply it by the length of that junction, and then you do it with all the other junctions. It takes no time at all. And there you have your heat loss. Ta-da! So what MBT have done is say, okay, we are providing a system rather than a piece of material. Therefore, we can calculate all this beforehand, okay? And then we can work with you on the design detail to help you understand how that is interpreted within your own design. And as a result of that, you can exploit much lower Y values. So to give an example, part L at the moment, typical Y value is 0.08. So you're having to add 0.08 onto your overall U values, okay? MBT system can be as low as 0.02, all right? So if you come to us and say, we want a U value, what's your wall build-up for a 0.2 U value? Well, we could say, another way of looking at it is you could actually increase your U value to 0.26 or thereabouts. SAP's a bit funny, so it's not complete exact, but it's thereabouts, because you're using an MBT Y value, okay? So it's that advantage of using SAP in a much more effective way. So you're delivering the same building performance, but your wall has just shrunk, okay, in terms of width, which keeps the developer happy because he ends up with more footprint, and keeps the contractor happy because he's spending less money, and the developer. So as a result, we've become much more commercially viable, if you like, rather than just the idea of, oh, it's nice sustainable materials. I'd just like to say as an aside, really, I don't know how much, the reason why MBT started off using natural, inverted commas, materials is not because they're warm and cuddly, although they can be. It's actually because they've got performance advantages that at the moment synthetics don't have. I don't know if any of you are involved in outdoor pursuits, but there's a product called merino wool, which is used in a lot of stuff like cycling and mountain biking and skiing and so on, which is a brilliant base layer, okay, as in it's the thing that's nearest your skin. It takes all the sweat away very, very quickly. You can wear the thing for a week. I've never quite managed this yet, but apparently you do, and you won't smell. It's incredible performance, and it keeps you incredibly warm. And there's no synthetic on the market that actually delivers that level of performance at the moment. Exactly the same with natural materials. There are dynamics about the materials that we use that you just can't get in synthetics, and I'll come on to that shortly. Air tightness we talked about. Again, because you're reducing your heat loss, your fabric heat loss. If you don't do anything about the air leakage, then you're kind of beginning to waste your time. So we really need to start driving down the levels of air leakage out of a building. And these two combined, low air tightness, which we can deliver because it's a system approach, okay, and low Y values means, again, you can help to relax the U values that you've got in your roof and your wall and your floor and even your windows, which are often the very expensive part, to help you achieve the same performance, and we'd argue in reality probably more likely, because it's more of a joined up process, than if you went down the more conventional route. That's a typical system. This is Pavel wall. It has two iterations. It's either on a steel frame or on a timber frame. It's either clad or it's rendered, or you can build a brick facade up the front if you want, but that's unusual. It has all these three performance elements that we talked about, particularly because it has the insulation running over the outside. The boards are tongue and grooved. They're easier to fit together. The waste is significantly reduced down about to sort of 2 or 3% because of the tongue and groove and the fact that they don't have to hit centers of the studs when you're actually on site producing these. You can even, the waste, you can actually shred up and dig into the flower beds, which has been attractive to certain contractors in terms of getting rid of landfill. And again, details where we're looking at air tightness detailing, principal thermal performance, and the battery's going flat, I think. and the non-repeating thermal bridging. Again, all details that we go through you. That's the simple bit. Keeping a building warm in winter is generally fairly straightforward, okay, but there's these three other dynamics we'd like to talk to you about as well. Health and comfort, about moisture control within the air that we breathe, fabric durability, and summertime overheating. There was a government report produced in autumn 2010 that said just this, that a new generation of sick buildings could occur, okay, if we don't deal with health and well-being of actually the building fabric and how we're doing with it. Actually, that perhaps this should be on the same level in terms of importance as carbon reduction. Interesting graph. I'll try and explain it. You've got 0% relative humidity down there and 100% relative humidity over there. So this is the air we breathe right now. And depending on relative humidity in here, is obviously just the moisture content of the air. It's relative because of the temperature. So the lower the temperature, the less moisture in the air. You've got various types and species of bacteria, fungus and virus. They generally thrive at either 0 or 100% relative humidity, okay? But they all tail off to almost non-existent at 50% relative humidity. Coincidentally, you and I are most comfortable at 50% relative humidity. Happy days. But it is interesting because suddenly we're switching from the idea that sustainability, so-called, and high performance is all about just low energy bills and ticking some carbon box, to actually producing a building that's far more comfortable to live and work in and far more healthy to live and work in. We've had guys that join the company and they go into buildings that have been designed as well as this, and they actually change their expression on their face as they walk into the building and go, wow, that's quite something. And they're not looking at anything, it's just the air that they actually feel. Fabric durability, moisture control. So this, I'll use a timber frame as an example for this. Here we have a timber frame. We've got studs, cross-section from above. We've got insulation between the studs. We've got OSB on the outside. That's to stop the building getting blown over in the wind for racking. Plasterboard on the inside. The moisture comes into the building fabric, and then because it moves through the insulation more quickly than it does through the actual OSB board, we get a build-up of moisture. So we say not to worry. We will line this building with a plastic bag to make sure that the moisture can't get in the first place. And that vapor barrier is, of course, fitted 100% correctly on site, and then it's never punctured in the lifetime of the building. I'll leave that one to you. What we find is that that doesn't usually happen. So what we really need is a system that allows moisture to get out more quickly than it gets in. So MBT systems, again, allow the moisture to get out once it's gone in more quickly. So in this case, what we do with a timber frame is we encourage get the OSB board on the inside. You can then tape the OSB board, and that'll actually give you an airtightness barrier, so you're saving on membranes. Batten it out for a service void and then plaster board. You've then got an insulation between the studs, in this case Pavaflex, and then over the top you've got another wood fibre board, which was the tongue and groove we saw earlier. That whole thing is fail-safe for moisture. Okay? You cannot get an excessive build-up of moisture, principally because you have a heat differential between the inside over here and the outside over here. And so long as the least permeable is on the inside and the most permeable is on the outside, you will find that you end up with a vapor open or breathable structure. In terms of MBT system, I want you to think of it slightly more different than just, look, here's a bunch of materials and you must use them in this order, in this way. It's more about a bunch of principles that we've been talking about here and actually bringing those to bear within a building and making sure the building physics works, rather than just, here's a piece of material, making sure that works. Okay, summertime overheating. This is becoming a biggie as well. 3 reasons why we get summertime overheating. Excessive gains from people and machines. That's usually more relevant to commercial rather than domestic buildings. Too much sun, okay, directly through the windows. That's mainly about building orientation, okay. And east and west particularly, actually, that's a killer. People usually just think it's all right, I'll stick a brise-soleil on, but it won't work on east and west elevations because of the angle of the sun in the sky. So south, fantastic. East and west, not great. You're perhaps looking at vertical elements or just maybe smaller windows. This is the last one, which is heat passing directly through the building fabric. Okay, we've referred to this as the decrement delay. So on lightweight structures, okay, if you've got a phenolic frame, say, within a given structure of a given thickness, then you might only have 3 hours before the heat energy from outside is actually permeating inside and heating up the interior of the building. Okay, an MBT system, same thickness, it'd be about 10 hours. Okay. And the reason for that is because people say, hang on, the building's insulated. I thought it kept the heat in, so it keep it. Well, the amount of energy that the sun throws on a square metre of your building from the outside during the summer is vastly greater than the small amount of energy that your little boiler throws on a square metre wall from the inside in the winter. So actually it pushes its way through the building far more effectively. Okay? So thermal mass is the key to keeping a building cooler in the summer. And the key way to introduce that into a timber frame or a steel frame, which has very little mass, is, like I said, with a system approach that we've talked about, because they have very high thermal mass in them. So keep your mass high, and that's the kind of thing that we're happening. So if you look at a quick example here, that's the external temperature, okay, the black line, so we're going up to about 35 degrees, so just emphasis, because it's very hot, that it's worthwhile saying. And on roofs and stuff, that's not untypical, okay, we forget that on terms of surface temperature of a black tiled roof, they get very hot indeed. That's a mineral wool example, the blue line, and this is a Pavaroof system, where actually, by the time the heat's coming inside, it's pretty much about midnight, which is probably quite useful because it might just turn up the heat, but the level of heat that's coming in is so much less than otherwise. So, just to go through again, we've got Paverwall, Pavaroof, Thermoplan. That's a quick example of what Pavaroof looks like. So, and I say again, this isn't the exact way it has to be. This is an example, but all the principles that we've talked about apply here. So it is vapor open, it delivers high performance in terms of energy saving down the side here, okay? It delivers vapor permeability, and it delivers summertime overheating. One thing I forgot to mention, going back to this slide with the bacteria and 50% relative humidity, that's got nothing to do with the fabric, okay? A breathable fabric will not help, okay, control the relative humidity, even if it's very breathable. Okay, it might, but less than 1%. Okay, so for all intents and purposes, ignore it. It's all about ventilation. Okay, and it's directly related to your airtightness. So you have a very airtight building. You need to make sure not only that it's ventilated at the right rate. Okay, the rates are much, much lower than the air leakage you've just prevented. So you're not kind of defeating what you've just achieved. But you must make sure that that ventilation is throughout the building. Okay, good circulation. Right, you might have the right ventilation strategy for the building, for the airtightness, but you've installed it in such a way that this half of the room actually doesn't get any airflow and that half does. Well, this will rise in RH and you will start having issues with mold and bacteria and all the rest of it. I should have said that earlier, but never mind. So fully vapor open, again, tongue and groove boards. This has a latex coat impregnated into it, so you don't even need a membrane on the top here. And because of the nature of the system and the board itself, it's got a very high thermal mass. So we're really mitigating against that summertime overheating. Same with the boards, and there's some examples. It could be clad, which you saw a moment ago, or rendered. If this is Thermoplan. So what we've got here, okay, is a simple monolithic block, okay? That's the outside, that's the inside, that's the block, okay? So on traditional masonry, you're replacing two cavity walls, ties, insulation you're trying to fit round the ties, cavity closures, all the rest of it. One block, okay? It's machined after firing, okay, to within a tolerance of less than 1 millimetre, okay? And then you put on the mortar, so you put the base coat down on about a 10mm mortar bed, but then thereafter you're only having a mortar of 1 mil thick, and it goes on with this hopper here. It either comes with mesh or without mesh. Without mesh, you're looking at runs up to about 25 metres before you need expansion joints. With mesh, about 40 metres, so reasonable lengths. There's no mortar in the perps, so it's actually a very quick build, as you can see from the video right now. It's actually quite fast, to put it mildly. It's actually 4 times faster, or up to 4 times faster than conventional build, and really delivers on the performance. You put plaster or render on the inside and the outside. Okay, you can clad it, but you need to put at least a parging coat, because then it delivers excellent airtightness. Okay, so it's very much this systems approach again. That's a typical use. That's in the Cotswolds. It's actually got stone clad on the other elevations, which you can have against it. You don't actually need a cavity unless it's very vapor closed granite or something. You can produce other iterations in it. It doesn't have to be a square monolithic block, or you can hybrid it, as in One Brighton, where actually the Thermoplan was used in the concrete frame, and then it was run over the outside with Paverwall and then rendered. So coming into land, we talked about the systems, we talked about the project manage approach, and we talked about the elements that we'll bring to bear on a particular scheme. So if there's a particular scheme that you actually want to engage with some of this on, or just explore it as an idea, then give us a call, and we'll initially talk about the performance target. What are you trying to achieve here? Is it building regs, or is it all the way up to some passive house standard? We deliver both on a regular basis, and because we've got this joined up process, we're delivering £1,000 a square metre built cost in Dorset for Passive House. So that's quite unprecedented, and it's particularly because there's this joined up thinking approach. U-value calcs, standard issue. Y-value detailing, we've talked about that, and this is all everything on offer. We'll actually do your SAP and your PHPP assessment if you want, okay? Or we'll work with the SAP and PHPP assessor to make sure that they understand how to gain the best advantage of the system. That's particularly relevant in SAP because it's not quite as clean as PHPP is. WFI calculations, we've talked about that before, so making sure that the building fabric is really going to deliver. BAB, because it's a system approach, we've actually got all of them certified, okay, by BBA, okay, apart from the Thermoplan, which has passed the affectionately termed kiss of death test, but has yet to receive its final approval, but we're told that's fairly imminent. They've all got LABC registered details, and of course they're all fully warranted.